No, 1 or 2 masses. Yeah. But yeah, they're.
Okay, so good morning, everyone. It's a real pleasure today to have Joris Witstok here talking about Lyman-α during the epoch of reionization. Joris is now a postdoc at the Dawn Center in Copenhagen, but before he worked and he did his PhD and first postdoc in Cambridge, working mainly with Roberto Maiolino's group, but also Renke Smith is an expert on dust and of course on reionization. So I'm sure it will enlighten us about this very interesting epoch, first epoch of the evolution of the first galaxies. So thank you, Joris.
Well, thank you so much, Roberta. And yeah, thank you for having me over here. It's my first time to Slovenia and it's been great so far. So yeah, today I'd like to talk a little bit about some of the work we've been doing on really probing this, the process of reionization by looking at the very most distant galaxies we can see with JWST. And I want to start, having moved to the Cosmic Dawn Center at Cosmic Dawn. So, of course, very early on in the universe, it was completely dark. And this all changed when the first astrophysical objects started to form. But we don't really know that much about the details of this process. So we don't know if it was stars or black holes that were actually the first to form. And when we can actually talk about these galaxies that started to appear. And you can see here in the simulation, this is basically a movie of reionization. So this is showing you the density of photons as they start to appear from the first sources. But of course, this is just one kind of rendering of this. And a lot of the details here depend a lot on these questions that we don't have firm answers to yet. And in a more schematic way, this is probably a picture you've seen before. So we're over here all the way on the right in the present day. And over here we have the Big Bang. The period that's kind of blown up here, what we're interested in is reionization, where we have the first galaxies have started to appear and start to emit these ionizing photons that form ionized bubbles, which eventually start to merge and then leave the universe completely ionized. So if we zoom in a little bit, if here the dark ages are actually, they look quite boring, right? But it's there already that the dark matter starts to form the skeleton of cosmological structure. And then, of course, once we get these first stars to form, there's two things that happen. They start to emit ionizing photons, and a lot of them, but they also very quickly produce heavy elements, so anything heavier than helium, carbon, oxygen. And that means we have this quick transition from the population 3, the very first metal-free stars, to population 2 stars. And then if we move over a little bit, you see actually within about 1 billion years of cosmic time, the whole universe had already been reionized. And so this means these first galaxies appeared really quite quickly, and they were very efficient at producing enough ionizing photons. What does this mean for us observationally. So this is just a nice cartoon to show if we look at a very distant background source like a quasar, then we might have a spectrum looking initially something like this. But you'll notice when I start playing this and the light starts to move through the IGM, the intergalactic medium, we have all of this absorption going on, which is due to the neutral gas that's still left in the IGM. And what happens is in this region called the Lyman-α forest, because of the redshifting, we get all these individual absorption lines initially. You'll see here in the region of the ionizing part of the spectrum, this gets completely absorbed quite quickly. And at the end, after traveling through the IGM for a while, we're left with something that looks a bit like this. But this is a quasar as it would be observed probably at a redshift of around 3 or 4. If you keep doing this and you push to higher redshifts, you might imagine eventually all of this flux is going to get completely attenuated and absorbed. So what we see when we look at the very most distant galaxies, when we're really probing into the reionisation era, we get a transmission profile that looks a little bit like this. So this is zooming in around the Lyman-α wavelength, the resonance wavelength. The different colors here are different sizes of an ionized region. So here we're really looking at a time where galaxies are probably surrounded by small regions where the universe has been ionized, and outside of it, it's still neutral. And you can see that as we move from the black line, which is having no ionized region, there's a lot of absorption, right? We have no transmission. As we move to higher and higher ionized region sizes, you get slowly more and more transmission. But in all cases, you have pretty significant, this is all well below 1, right? So the spectrum really gets attenuated even beyond redwards of Lyman-α, which is due to the damping wing profile. And
so,
yeah.
Just asking, it looks like even, it's not asymptotic to 1, even at
yeah.
So you get a DC offset regardless.
Yeah.
At all.
And this is just due to, even if you're inside a very big ionized region, at some point there will be some patch of neutral gas left if you're above redshifts of 5 or 6.
But this is then what you do. Is this ISM or this is IGM?
No, IGM.
Oh.
Yeah, this is purely IGM. Yeah. But so this is, really the highest redshift regime. You only start to notice this, beyond the redshift of 5, something like this. I'm actually going to go back to slightly lower redshifts because this whole concept of IGM transmission was recognized really quite early on. So it was only, basically a few years after the first realization that these sources we were seeing, very bright quasi-stellar objects, were actually very distant quasars. That there was a paper by Gunn and Peterson where they already noted that the continuum of these very distant quasars actually continued bluewards of Lyman-α, and that this tells us very, very fundamental information about the state of the gas in the intergalactic medium. Now, this was at, you see, a very distant source of a redshift of 2. So, of course, we have moved quite a lot since these initial papers. And so this was an overview of spectroscopically confirmed galaxies just before we started observing with JWST. So this is one overview focusing also on what ALMA was showing. I won't talk too much about ALMA today, but very happy to to talk about some of this as well, because I think ALMA is really still a key player next to JWST. But you'll see, ALMA was able to identify quite a lot of galaxies sort of between redshift 4 and 6. And then as we got above redshift 6, there were some Lyman-α emitters that were able to provide a spectroscopic redshift. But ALMA also was able to push into the epoch of reionisation, really, out to redshifts of about 8 or 9. And you see all these background points. These are photometric candidates from HST. So there's lots of them, but we could only spectroscopically confirm so many of them. But this has completely changed with JWST, as you know. So the question before the launch was, of course, what is beyond these boundaries? And this is just one rendition, a paper that came out towards the end of last year, which is already outdated. But all of these solid points are now confirmed galaxies at redshifts beyond 8, some even beyond 10, and many, many more candidates from photometry. So today, I'm just going to focus on one of these surveys, which is the JADES, so the JWST Advanced Deep Extragalactic Survey, which I've been part of. This is an effort led by 2 GTO teams, so the NIRCam and NIRSpec teams. And really, the idea is to combine the strengths of these 2 instruments. So you'll see here some nice images from the NIRCam instrument in the Hubble Ultra Deep Field. So this is the JWST view of the HUDF. But what we do then after getting this imaging is, of course, we place many slits using the NIRSpec multi-object spectrograph and try to select as many very high redshift galaxies to get spectra for. Now, this has led to many of these very beautiful spectra. So this is just one example of a redshift 9.4 galaxy, which in this case has gone over 100 hours of exposure time in different spectroscopic modes. And you see that all of these features, this is not noise. We're actually detecting individual emission lines in the rest frame optical, but also in the UV. And this is really allowing us not just to spectroscopically confirm these sources, but actually really dig into the details of the physics going on in these early galaxies. So very shortly after the first data came in, we were able to find, in this case, 4 sources beyond a redshift of 10 and confirm them with NIRSpec. So this is just what those spectra look like. Now, what you'll notice is that in all of these spectra, the one feature that really gives us the confirmation is just the Lyman break, right? So it's just this step function, which is due to the absorption by the IGM, that gives us the redshift. But there's actually no emission lines detected. So we're not able to measure, for example, abundances of elements or say something about the conditions of the gas. People tried following up other sources that were confirmed by JWST and tried to see with ALMA, for example, if we could find any emission lines. But that all proved pretty tricky, and I'll get onto why, one of the reasons why that may be in a second. But then another round of imaging and spectroscopy followed, and you'll see this is a case that was a little bit more dubious, because this very red source here, that's the very distant galaxy. There's a foreground source which sits just right next to it, so it's a little bit trickier to tell actually what the redshifts are. But we got spectra for both of these sources, and it turns out they're both at a redshift of about 14, or in this case, even a little bit above 14. And there is actually this, well, somewhat tentative initially C3 line starting to peek through. We now know, because of ALMA, that that is actually the carbon-3 line. But so we're able to push to higher and higher redshifts. And among with very many other sources here, this is just showing, again, the confirmed redshifts, or in this case, age of the universe as a function of brightness. The confirmed sources with JWST are starting to kind of become more and more luminous than we might expect. And you can tell this by especially this source at redshift 14, even though it's not quite as luminous as, for example, GNZ11, which is this very famous HST detected galaxy. You can tell from this dashed line, this is more or less how the halo of a galaxy, the dark matter halo a galaxy would sit in, how this would evolve as a function of time. And you see, if we just follow some very simple scaling, this would actually be, orders of magnitude brighter than any of the galaxies we see at slightly lower redshifts. So definitely something is going on at the very high redshift regime we're seeing. Somehow galaxy formation is extremely efficient, and there's been many, many ideas about how we can change our models basically to accommodate this. Now, one of them, of course, is changing cosmology itself, which I think the consensus is we don't really have to turn to this just yet. AGN, of course, could play a role, but definitely in the case of this galaxy, we know this is actually quite extended. So AGN, an AGN contribution can't be the dominant factor behind the very high brightness. Top-heavy IMF could be one option. There's bursty star formation. We could, again, contribute somewhat to sort of making these galaxies look a bit brighter when they're in their burst phase. There could be a difference in how dust absorbs some of the light we're seeing, and the efficiency of star formation itself could just be enhanced somehow. Maybe the feedback isn't quite as strong yet. But all of these, of course, would have pretty large implications also for reionization. So what are all these observations telling us about the first stages of reionization is the question. And so what I'll be talking about mostly here is these Lyman-α emitting galaxies. Now, the reason we're interested in these is if you look at Lyman-α emitters, which are the red stars in this graphic, as we move from early times to late times, you see these really they trace the emergence of these ionized regions, these ionized bubbles, which are the light regions in this plot. And they actually have they're very powerful in constraining exactly how reionization happened. For example, whether we look at reionization as it would be primarily driven by low mass galaxies, where you see this specific pattern, and if you compare that to reionization driven by the more massive, the brighter, high mass galaxies, you see, especially at sort of early times, there's a very different sort of clustering and spatial distribution of these Lyman-α emitting galaxies. Now, just to remind you, why is it that specifically Lyman-α is such a good tracer of this process? This is because this IgM transmission I showed you earlier, and the fact that basically all of these galaxies, because they're so young, they're metal poor, so they just produce a lot of ionizing photons, which mostly are being reprocessed into recombination emission. And so Lyman-α intrinsically is very bright, but depending on where these galaxies are sitting in the ionized or not yet ionized medium, we'll see very different profiles when you actually observe them. So this is just showing basically if you're inside an ionized bubble, you have quite a bit of transmission, and you might see even some of the blue Lyman-α flux. Whereas if you're closer to the edge or even outside of the bubble, all the Lyman-α basically gets absorbed. And this has been observationally seen for a long time, and so we can actually quantify that as you go above a redshift 6, the fraction of galaxies that show Lyman-α starts to drop very quickly. And this is one of the main ways that we can tell sort of when this reionization process was happening. With JWST, we're actually able to see something else, which is signs of very, very dense neutral gas, not in the intergalactic space, but probably very close or even in these galaxies. And the way we see this is by these very strong damping wings. So the blue lines here are showing what you would expect just from a completely neutral IgM. But you see the spectrum actually is more absorbed than this. And so you have to have some extra dense gas sitting somewhere close to the source. It could also be that nebular emission becomes stronger, which kind of mimics the same effect. But in any case, with JWST, one of the things we're now able to do is really push to very high redshifts where we can see these Lyman-α emitters and actually correlate them with the distribution of neighboring galaxies. So in this case, we see a redshift 7 Lyman-α emitter, which must be sitting in this quite large ionized region, and it's actually located exactly where there's this overdensity of galaxies, which of course is just not a coincidence that we're seeing this, but all these galaxies probably contributed to creating this quite early on, which then allows us to see Lyman-α. So another, it was really quite surprising therefore that when we looked at this GNZ11 at redshift 10, it actually showed some Lyman-α emission, which was completely unexpected. So previously, the highest redshift Lyman-α emitters were around redshift 8, 8.5, and there were very, very few of them. It was very hard to find Lyman-α there. And so it was completely unexpected to see this at redshift 10. Since then, we found quite a few others. So in this paper, we focused on these three, which were all above a redshift of 8. So basically doubling the number of these very, very high redshifts Lyman-α emitters we knew. And the fact we're seeing Lyman-α this early on again is a signature that these are probably the galaxies that are sitting in some of these very early ionized regions. But with NIRSpec, we can do much more than just looking at Lyman-α. So this is just showing you the full spectrum of one of these. One of the things, for example, we can say immediately is there's this spectral discontinuity at the Balmer limit. And so this is showing there is very strong nebular emission. But it's also showing these very high ionization lines. So carbon-4, for example, which can only come from very hard radiation fields. So you need more than 54 electron volts to ionize this state of carbon. So what is all of this telling us? Potentially, this could be starting to answer some of these questions that I was talking about earlier. For example, about AGN. So again, going back to GNZ11, this is actually one of the sources where we suspect there might be an AGN present already. There's many reasons for this, and I'll quickly go through them. So there's very high ionization lines. There's line ratios that point to very, very high gas densities and very deep C4 absorption that we only see basically in AGN. But of course, the question is, how can we select these in typical, less bright galaxies? And this is an issue because when we try to apply these classic diagnostic plots, like the BPT diagrams, basically all of the galaxies end up in the same location. So we can't really distinguish very well between AGN and star formation. There's also some very puzzling absences of, for example, X-ray emission when we look at some of the JWST identified AGN. And I'll get back to this. This might prove some kind of connection between the fact we're lacking all this X-ray emission and also the fact we're seeing in many of these broad line AGN that there's actually absorption in the Balmer lines, which shows us, again, there's this very, very dense gas close to the black hole. So just in terms of the practical standpoint of how can we identify potentially AGN is to go into the UV and use some of the UV diagnostic plots. So this is what we did for some of the high redshift Lyman-α emitters. And there's a lot of points on here, but just to point your attention to this one Lyman-α emitter, which was the brightest among the ones we identified, you can see this one is actually consistent with star formation. But it's different for one of the others, so that might actually have some contribution from an AGN. And by coincidence, or maybe not, this is also the source that actually is the most efficient at producing ionizing photons. So putting it all together, I think AGN are definitely not ruled out as having some contribution, at least in these very early Lyman-α emitters. We can also try to measure some of their stellar properties, now assuming that most of the light is coming from stars. And, well, perhaps unsurprisingly, this is showing that in these very early Lyman-α emitters, we see a very strong upturn in recent star formation. So these are, we're basically seeing very, very young stellar populations in here. The other thing, if you look at some of the imaging, is that they actually seem to often have these neighboring sources, which are a bit fainter, a bit harder to observe. But potentially this could also have a role, right, if these are merging systems that are somehow stimulating new bursts of star formation. There's another thing we noticed about how compact these sources are. So if we look at how intense their star formation is in terms of the surface density, and you compare this to the Lyman-α strength, you see our points here actually line up quite nicely in this relation where the more compact this star formation is, the higher the Lyman-α we observe. And especially this very, very bright Lyman-α emitter has a star formation surface density that's way beyond any of the local, very extreme analog galaxies. And so one of the things that might help Lyman-α escape is this very compact mode of star formation, which maybe sort of concentrates the feedback and clears neutral gas around the galaxy. We can also test how the IGM actually attenuates Lyman-α. So I won't go to the details of this, but if you know how much ionizing photons they're producing, which we can measure, you can actually measure how much Lyman-α is escaping. And then we can actually see this kind of trend where if we go from low to high redshift, so the blue points to the red points, their Lyman-α escape fraction is actually nicely decreasing, as you would expect going into a more and more neutral IGM. And again, this very bright Lyman-α emitter is kind of an oddball here, showing a very, very high escape fraction, even though it's at very high redshift. So this means it must be sitting in one of these early ionized regions. Okay, in the last few minutes, I just want to focus on then really pushing the frontier of all of this. So this is a nice overview we made from the JADES origins fields, which is one of the regions where we took a lot of very, very deep imaging across multiple bands, really to try to push to the very highest redshifts we could. And these 10 or so sources are basically the most robust candidates that were identified. Now, the redshift 14 galaxy that I showed earlier, so currently the most distant one, that's up here with the foreground galaxy next to it. But it was actually another source, so this is JWST 14, but it was a different source, the one at the bottom there, which was a more robust candidate around a redshift of 13. A very compact source. So we decided to put this on a slit of NIRSpec and get a spectrum of it, and this was the result of what we got. So it's quite a bit fainter, but we were able to identify, you have this Lyman break again. But what's very surprising is you also see this very, very clear emission line. And so all of this is very quite puzzling. So first of all, yeah, there is the redshift, which we're able to confirm at a redshift of 13 because of the Lyman break we see. But at the same time, there's this quite smooth turnover of the spectrum, which needs, again, this very dense gas. But while we're seeing this, there's also this line which cannot be anything else than Lyman-α at this location. So the question is, how do we put all of this together? Well, first of all, we wanted to make sure that this is really what we think it was. So you know, one of the options is that this could be a brown dwarf, and somehow this is just a very, very local source. But this is very clearly not the case. Just from the photometry, this is very confidently ruled out. It could, of course, be contaminated somehow in the spectrum, but we carefully checked this, and there's no contamination there. And also, the emission line feature actually happens very consistently through all the exposures we have, and there's no outliers in any kind of regard. So it's definitely not some kind of issue with hot pixels or outliers. I can also say this isn't published anywhere, but we went back to this source among many others this past January, and we got another spectrum, a deeper spectrum, which shows exactly the same result. So we have this pretty blue continuum with a very, very strong emission line. What's a bit of a shame is that there's still no other emission lines that we can detect confidently. So the exact redshift is still a little bit hard to measure because of the resonance, the resonant scattering that Lyman-α can undergo. What we can say, though, is that because of the medium resolution spectra, we know the Lyman-α line is probably broadened spectrally. So we don't detect it in the medium resolution, which is completely expected as long as the line is broadened a little bit. Just because these medium resolution spectra are much, much shallower. So one of the first thoughts we had was to actually link this to a slightly lower redshift example that was published in this paper, showing this similar kind of pattern of very strong Lyman-α emission with this strange turnover of the UV continuum. And this would be really interesting because if this is due to the nebular continuum, as is argued in this paper, you actually need a very, very top-heavy IMF to have very hot stars completely dominate your spectrum. But it doesn't seem to work as well for our Lyman-α emitter, just because the spectrum is so blue that it actually rules out nebular continuum being the dominant light that we're seeing. And so the other option then is to have this damped Lyman-α absorption, so having the very strong damping wing absorption, at the same time as having emission. Now that sounds a little bit odd, of course, having very strong absorption and emission at the same time. But it could actually be pretty much expected if you have a very low dust content. So if there's no dust, Lyman-α is able to scatter out through very dense gas even. And so really that would mean we're tracing both the ionized and neutral phases of the gas through the emission and the absorption at the same time. What is also striking about this is that if you take just the Lyman-α luminosity and you put in a very, very reasonable estimate of how much the IGM will absorb some of the Lyman-α, you actually see immediately that you need a very, very high efficiency of ionizing photon production. So just to put this into context, the 10 to the 26 is kind of the limit of what stellar models are able to produce. And we find a value that's something like 0.5 dex higher than this even. There's also a very, very blue UV continuum. So this, as I said, it means you can't have very much of a nebular continuum. And so probably a lot of the ionizing photons are actually escaping the galaxy, which works very well together with seeing Lyman-α, because if ionizing photons are escaping, that means it's probably powering one of these early ionizing ionized bubbles, which then helps the Lyman-α become observable to us. And just to show that actually empirically, if we look at some lower redshift examples, we actually see similar features both in star formation driven scenarios. So these are dwarf galaxies where we see a very strong Lyman-α emission line at the same time as having damped Lyman-α absorption. But this is also seen in quasars. So here we have, again, a very strong Lyman-α line, which is sitting in one of these DLA troughs. Now, this one also, again, shows this absorption in the H-alpha line. And so that's very clear evidence that there must be these very dense gas clouds very close to the source. So, you know, motivated by these works and how they're able to explain seeing this kind of a spectral shape. This is the very schematic picture we're proposing, which is, you know, there's basically two options for having a source powerful enough to produce the amount of ionizing photons, either being an AGN or very massive stars, which are then surrounded by some kind of inhomogeneous neutral gas distribution. So either we could have some kind of ionization cone where we're looking along the dense gas that's streaming in sort of along the plane, or we're just in a very inhomogeneous ISM where the Lyman-α is able to scatter out. So with that, I'll conclude by saying that all of these observations of Lyman-α are really giving us very important insights into how reionization is progressing. I've shown you some results of 4 very distant Lyman-α emitters, which are all very, very highly star-forming and low-mass examples. And there's now this quite puzzling population of systems where we have both Lyman-α emission and what seems to be very strong absorption, including in one of the highest redshifts sources we know. So I'll stop there and I'm very happy to take questions. Thank you.
Thank you very much, Joris. It was extremely interesting, very interesting. Do we have any questions?
Well, this is excellent because I'm scratching my head already the entire time. I'm trying to reconcile this Lyman-α emitter, you know, having both absorbing and emitting gas at the same time. I find it sort of impossible. Also, in this picture, right, what you need is for this Lyman-α to be scattered, to be redshifted, so that it gets out of IgM.
Yeah.
So, I mean, and of course, lower redshift things you can do that because you don't have the IgM, but you know, I find it.
Sure.
Of course, we need the systemic redshift measurement. That is going to tell us a lot of things. But I think perhaps, have you looked into, like in your last model, you alluded that you have channels of Lyman-α escaping parts versus channels of absorbing, and how many of each would you need in order to reproduce both the damping wing and Lyman-α escape?
Yeah, I mean, this is really you're hitting the nail on its head. Yeah, having the systemic redshift, of course, would be very helpful in pointing, you know, to exactly how much the IgM is going to impact the Lyman-α emission. Maybe I'll start by saying that when we have this, so Lyman-α resonant scattering is a very complex process. But what it does do is, of course, when you scatter a lot inside the galaxy, you're able to shift your line into, away from resonance already. So this very, very well works together with being able to transmit that same Lyman-α line through the IgM. Because if you're already starting 300, 400, 500 kilometers per second redwards of the resonance, then that really reduces the amount of IgM transmission. Yeah, but now your DLA hits, right? You clearly need a DLA, which is close. So I mean, you shifted exactly in the point where it's going to get absorbed again. So. Yeah, no, but I mean, I agree. It seems very counterintuitive, but I mean, clearly from low redshift observations, this can happen. So there are ways where the continuum, because it's mostly the continuum that experiences the DLA absorption, even though somehow the Lyman-α emission is able to transfer out of this dense medium. Very strongly so, right? I mean, the line is strong. This is also the very puzzling thing. So it doesn't seem to be very absorbed. Yeah. So this is why I said, you know, if we just imagine a cloud of very, very dense gas without any dust, I think this is the most sort of appropriate. It's neutral, it's going to absorb Lyman-α very quickly, right? You need the density of 10 to. Well, that's the thing. It only resonantly scatters, so it absorbs it, but it emits it right away. So it can actually scatter out, even though it takes a lot of, you know, it'll be absorbed, emitted, absorbed, and so on. But that is one of the mechanisms that can kind of shift. If more of these scattering events happen, that'll gradually shift your peak, potentially to redder wavelengths. So. And my more mundane question is regarding your compactness measurements. Yeah. Right?
can't help but wonder if some of this can be due to the effect that NIRSpec slits are so small, where you had a graph of equivalent bit of Lyman-α versus compact list of galaxies.
Yeah.
I mean, you might be just seeing better the things that are compact in Lyman-α because your slits are small. So you might be more efficient just based on your observations.
Yeah, that's a good point. What I think is quite noticeable, at least, is that just leaving aside the Lyman-α, if you take the star formation rate density that we observe, this is really, as I said, these are, green pea galaxies and so on. So very, very highly star-forming systems. And some of the sources we see at higher redshifts, they're well beyond, orders of magnitude above this.
My point is regular galaxy, which is not as compact, might also have the same Lyman-α. It's just broad, wider, more distributed, and so both from the fact that you have a narrow slit and the fact that it's low surface brightness, you might not be able to observe it.
No, that's a very good point, and this is why, I think doing things like counting the fraction of Lyman-α emitters. And using that to constrain reionization can become quite tricky. But just having individual examples like this where you do see very strong emission, I think it's clear that there's not, it's still contained in a pretty compact region.
But the measure here is star formation rate, surface densities. These galaxies, have to be resolved, right?
Yeah.
Yeah, all right. And then, this star formation rate, surface density is sort of averaged over the whole galaxy?
Yeah.
Or can you do more specific studies of a particular, very star-forming region inside the galaxy or something?
Yeah, that's a good question. We didn't do a spatially resolved modeling in this setting, but we just kind of took the average.
So related to this, can we then conclude that small compact galaxies in general have higher escape fractions of Lyman-α, or no?
Well, this is the kind of empirical evidence.
Right.
It's just whenever we see Lyman-α, it does happen in these very compact star-forming
But it might be
regions.
partly due to observational
Yeah.
effects, right?
Okay.
Yeah.
Just
I'm
balance.
worried.
Mm.
Well, you see them in a compact because it's easier to observe it, but there might be also not so compact galaxies that equally produce Lyman-α.
That still have the same escape fraction in
Yeah.
a sense.
But you just don't measure it.
Mm-hmm.
Yes, nice.
Well, dust obscuration torus, that's a normal feature in low
Mhm.
redshift AGN. And in your next to last slide, apparently this counts would be limited by 11. So I just wonder, can you confirm that this dust torus is already in place at such high redshifts by, I don't know, maybe future observations of polarization or something like that, observations of polarization? That's a standard way to do it in low redshift.
Yeah. I think at these very high redshifts, we'll have to probably resort to slightly more indirect measures, just because, it takes JWST to even detect them, and even then we're kind of limited by the signal sometimes. So I think, we'll have to come up with, and people are looking into this, I think, quite a lot by looking at things like the self-absorption in the Balmer lines, and sort of using that to figure out what are the geometries that we need to explain what we're seeing. But I think this is a very interesting question, is what does the geometry of accretion disks, does it change at all, and does that explain some of the things we're seeing?
So for example, this drawing, it's a schematic drawing, but don't we expect also to observe some AGNs where we observe through the ionization cone, at least a portion of them?
Mm-hmm.
For example, how many
yeah, you'd need pretty large samples to start doing that. Just the kind of motivation behind this picture is that when you look at a larger, say, all the galaxies where we do have spectroscopic conformations above a redshift of 10, it does seem like there is some distribution of the DLA column densities. So some of them show very, very dense gas along the line of sight, causing a very smooth break. But then others don't seem to show any kind of evidence for this. So, of course, you would be influenced by sort of the viewing angle in that case. I don't think we quite have enough statistics to do like very detailed sort of opening angle studies just yet, but I think.
What do we expect to see if we observe through the ionization cone, for example?
Yeah, no, I think you would be able to start to see a specific distribution depending on, yeah, the exact opening angle and so on. I should also say, one thing is, you know, this ionization cone, it's drawn here for the AGN case, but you might very well have a similar geometry if you have a very dense, a very compact star cluster. You don't necessarily expect, everything to be nicely spherically symmetric. So it could be that you have a similar geometry just by having a, very compact star cluster.
Okay, and you absolutely need spectroscopy to identify AGNs.
Yeah, yeah.
Oh, okay. Okay, so questions are over, basically. Okay. So we thank Joris again for the beautiful presentation.
Thanks.